In a previous video, we discussed using permutations and combinations to find the cardinal number of complicated sets. To find the probability of an event, we need to know both the cardinal number of the event set and the cardinal number of the sample space. So it makes sense that permutations and combinations could be useful in probability. Consider the following example. Suppose a company has 10 engineers and 12 marketers. And suppose that they want to make a 4-person committee. And suppose that they do this randomly. So they just take the 22 names, put them in a hat, draw 4 names out. Well, what's the probability if they choose them randomly that they'll have 2 engineers and 2 marketers? So we'll let A represent the event of having 2 engineers and 2 marketers. And our question is, well, what's the probability that A occurs? To do this, we'd have to count up the number of ways that A can occur and divide it by the total number of possible ways that the committees can be built, so the total number in the sample space. From our previous section, using permutations and combinations, we know that in a committee, order doesn't matter. So we have 2 decisions to make. First of all, of the 10 engineers, we need to choose 2 without order, and of the 12 marketers, we need to choose 2 without order. And for the sample space, there are a total of 22 people, and we're choosing 4, which gives us a probability of 0.4060 approximately. So there's about a 40.6% chance that this 4-person committee would have 2 engineers and 2 marketers. An example of how something like this might be useful is suppose that they randomly choose this 4-person committee and the engineers do the choosing, and they say, trust us, we've done this randomly. And suppose that the committee is formed with 4 engineers. Well, what's the probability that would happen if the members of the committee were really chosen randomly? Well, the probability that we have 4 engineers, well, first we have to count up the number of ways we could get 4 engineers. So out of the 10 engineers, we choose 4. And out of the 12 marketers, we choose none. Then we divide this by the sample space. Out of the 22 people, we're choosing 4. If you work this out, you'll see that it's approximately equal to 0.0287, which is roughly a 3% chance. So it's very unlikely that 4 engineers would be chosen for this committee. And if the engineers are always choosing the committees, and things like this happen frequently, the marketers can start to complain that this really isn't being done randomly. Or at least, most likely, is not being done randomly. Now in the example we just did, this part, the 12 choose 0, wasn't necessary since 12 choose 0 is 1, and anytime you multiply by 1, you don't change your number. But we wrote it in there for completeness so that you can see that we were choosing 4 engineers and no marketers. Next, let's look at an example of the probability of being dealt a certain poker hand. If you are unfamiliar with cards or poker hands, take this moment to look in your textbook and read about the different types of poker hands, as well as what a deck of cards looks like. So given a standard 52-card deck, suppose that you are dealt 5 cards randomly. The question is, what's the probability that you're dealt a full house? To find the answer to this, we would need to know the number of ways that we could be dealt a full house, and then we would divide that by the total number of different 5-card poker hands we could be dealt. When trying to count the number of ways we could be dealt a full house, you should consider trying to make a full house from a standard deck of 52 cards, and ask yourself, what decisions do you need to make if you want to build this full house? So one decision we would need to make is, what are we going to have for the 3 of a kind? So is it going to be 3 aces, 3 2s, 3 7s? And when making that decision, there are 13 different ranks to choose from, and we're going to choose one of those ranks. Next, we could choose which of the suits we're going to have for that rank. So we chose a rank, imagine kings, and we wanted 3 of those kings. So there are 4 kings to choose from, and we're going to choose 3. Next, we're going to choose the rank of our pair. Now we can't have the same rank as the 3 of a kind. So there are 12 ranks to choose from, and we'll choose one. Maybe these are 7s. Well, there are 4 different 7s, and we need to choose 2 of these. And out of the 52 cards, we were choosing 5. Now that's just one way to solve this problem. Another way to solve this problem is we can actually choose all of our ranks first, and this is a good idea oftentimes, and we'll see this in the next example. So we know that we're going to need 2 different ranks, one rank for the 3 of a kind and one rank for the pair. Now we have to ask ourselves, does the order in which we choose the ranks matter? Well, if you think about it, it does. Because the first rank we choose, we're going to have 3 of those cards. In the second rank we choose, we're going to have 2 of those cards. So for example, if we choose kings and then 7s, that's 3 kings and 2 7s. But if we choose 7s and then kings, that's 3 7s and 2 kings. So the order did matter. So of the 13 different ranks, we're going to pick 2 of them in such a way that order matters. So again, imagine that we chose kings, then 7s. So of the 4 kings, we're going to choose 3. Really, we're choosing their suits. And of the 4 7s, we're going to choose 2. And out of the 52 cards, we've chosen 5, which is a probability of approximately 0.001. Now let's consider the example of finding the probability of being dealt 2 pair. Based on what we did last time, you might try the following. Take the 13 ranks and choose 1 for your first pair, and then of the 4 suits, choose 2 suits. Of the 12 remaining ranks, choose 1 for your second pair. Of the 4 suits, choose 2 suits. And of the 11 remaining ranks, choose 1 for your 5th card, and you only need 1 of the 4 suits for that 5th card. And then out of the 52 cards, we're choosing 5. Unfortunately, it turns out that this is not the correct answer. The problem with this solution is in the numerator, the number of ways we can be dealt 2 pair. Notice that we chose the first pair, then we chose the second pair. So we said, suppose you draw a pair of kings followed by a pair of jacks. We're saying that that's different from drawing a pair of jacks followed by a pair of kings. But it's not. It doesn't matter what order the pairs come in. See, with the full house example, we were able to choose the 3 of a kind first and then the pair second because it really did matter what order they came in. Kings followed by jacks would be 3 kings, 2 jacks versus 3 jacks and 2 kings. But in this 2 pair example, we can't choose the ranks one at a time. That's choosing them in order, and it says that that matters. So first, let's cross this out to make sure we don't use this example. Now let's see how we could do this correctly. This is where the second method for the full house will work. We need to choose our ranks for our 3 cards. Now let's see if order matters. For the ranks of the pairs, order doesn't matter. Kings and jacks, jacks and kings. They're both 2 pairs. Now the order of choosing the 5th card does matter because the 5th card we're only going to have 1 card. So for example, if we say kings, jacks, 7, that's different from kings, 7s, jack. That last card makes a difference. So we'll begin by choosing the ranks for our 2 pair. There are 13 ranks to choose from, and we will choose 2 ranks without order. Now, for the first rank, maybe the kings. There are 4 kings to choose from, we'll choose 2. Then for the jacks, there are 4 jacks to choose from, we'll choose 2. Now, there are 11 ranks left, and we will choose 1 for our 5th card. And there are 4 suits to choose from, and we need a single suit for that 5th card. And out of the 52 cards, we're choosing 5. And if we work this out, we see that it is approximately 0.0475. About a 5% chance that we'd be dealt 2 pair in 5-card poker. Now in the method we were starting to use for the 2 pair, we could have corrected the numerator by dividing out the number of ways we could order the 2 pairs. But I personally find it simpler to choose the ranks without order to begin with. At this point, you should pause the video and look in your textbook at the examples concerning lotteries and Keno. You'll find that lotteries and Keno are very similar to each other, and in fact they are very similar to the committee problem we did in the beginning of this video. In the previous video, we found that the probability that an event occurs plus the probability that the event does not occur equals 1, but we never actually used that fact for anything. Well, let's look at an example where complement events can be very useful. Consider the following example. Suppose you're standing in a room with 29 other people. And the question is, well, what's the probability that 2 or more people in the room have the same birthday? So again, we have 30 people, and we'll let E be the event that 2 or more share a birthday. And so we're trying to find the probability of E. And we could do this by counting up the number of ways that E can occur divided by the total number of outcomes in our sample space. So the total number of ways that 30 people could have birthdays. Well, let's start with the sample space. The number of ways that 30 people could have birthdays. Well, we could use the fundamental principle of counting. We can't use just combinations or permutations because birthdays can be repeated. So if you think about it, we have the first person, the second person, etc. And each of these people have 365 different birthdays to choose from. So this is 365 raised to the 30th power, whatever that number equals. Next, we need to count up the number of ways that the event can occur. Now here's where we're going to run into some trouble. We could count the number of ways that 2 people share the same birthday. But then we'd also need to count up the number of ways that 3 people share the same birthday, or 4, or 5, or 6. Or even worse, we could have 2 people sharing a birthday and 2 other people sharing a different birthday. 2 and 3, 2 and 4, 2, 2 and 3, 2, 2 and 4, etc. You can imagine how complicated and long this would be. In fact, most likely, no matter how hard we tried, we'd forget a few. So this is not going to be something we can solve directly. On the other hand, let's look at the number of ways to count up E complement. So first of all, what is E complement? If E is the event of 2 or more people sharing a birthday, then E complement must be that no one shares a birthday. Now that's something we can count. There are 365 birthdays to choose from, and we are going to pick 30 of them in order. So why are we using a permutation and not a combination? Well, look at the way we built our sample space. We chose each individual's birthday one at a time. We chose them in order. So our sample space is counting order. Therefore, our events must also count order. Another way to think about this is each person is an individual. So if I choose birthdays, I need to know which individual gets which birthday. So that tells us that the probability of E complement is 365 pick 30 divided by 365 raised to the 30. So we can find the probability of E by solving for it in our formula above, and that's equal to 1 minus the probability of E complement, which is equal to 1 minus 365 pick 30 divided by 365 raised to the 30th power. And if you work this out on your calculator, you'll see that it's approximately equal to 0.7063, or roughly a 71% chance that 2 or more people share the same birthday. I'll bet that you thought it was a lot lower than this before we started the problem.